being publicly streamed.
I think this is the paper, right?
Sir, did you compile the notes?
Oh no, I haven't. Oh no. Okay, I'll send you basically the ones in Good Notes and the ones in OneNote. I'll send it later. Okay,
Okay.
I'll send it to you after class because I'll keep on forgetting. I know I have so much work today and these days that I don't know what's happening. All right, so starting with this now.
So can we solve February March 2023?
We are doing it on Monday. Okay, instead of that
Oh,
paper. Yeah. All right. Is it okay with you?
okay, sir, no problem.
Okay. So then let's look at it says define gravitational potential. Okay. You guys already know. Work done. Per unit mass. And then, Faisal, can you hear me? Faisal, are you there? Can you hear me? Okay. So, Faisal, at the end of the class, please stay back. I'll tell you the timeline we're following for the paper. So, what you're going to do is you have to solve the paper with timing yourself, right? And coming into the class later by submitting. Okay. And then you check and ask whatever you have to ask. Okay. Do you understand what I'm saying? Okay. So, then work done per unit mass in moving mass from infinity to this point. So this is like 2 marks. And now it says you need to basically show that. Fine. This is gravitational potential energy, right? So gravitational potential is work done per unit mass. Okay. So it means the work done you do is the gravitational potential energy is potential times mass. So what is potential really? It's gm over r minus n times m. So you get gmm over r. So that's what you need to do.
Sir, so in that question, we have to just show how they derive the equation.
Yes, only that.
Oh, okay.
This is a path of comet. It's going, coming, back, whatever. Calculate the magnitude change in gravitational potential of as it moves from x to y. X to y. Interesting. You have the speed, you have the mass, your star mass, right? We got to find the change, right? So to do that, I think it's better to we'll use the same equation, gmm over r. So we're gonna take this 6.67 times 10 raised to minus 11 g times the mass of the star was this one, 1.99 something, 1.99 10 raised to 30. And the mass of the comet was 2.20 times raised to 14. And we're going to find the change in distance, right? So the smaller distances, like it says at point x, the distance this, and point at this point the comet distance is this. So we're going to use this first. 6.38 times 10 raised to power 10 minus, and then minus. Writing this sign is very important. You have to, in fact, like don't write all the values again. We can do it like this, please. That's easier to manage. minus 8.44. Okay, let's put minus in.
Sir, why are we putting minus before the actual equation, like the whole formula?
Because there is a minus sign here. Gravitation potential is always minus, no matter
Okay,
what.
so okay, and then can you explain this method? What you're doing again?
What I've done now?
What? Yeah, the bracket part.
Okay. So basically, I had to find the change in potential. Change in potential was minus Gm m over r, right?
Yeah.
And minus like Gmm r1 and Gmm over r2. Do you get it
Yes.
as a minus, right? So what I've done is instead of doing this, I have tried to put like I have taken the top values as common and then the inner values as this. You get it? I know.
Okay. Yes.
Just to avoid writing this much again. Like I don't want to
Mm-hmm.
do it. All right.
Okay.
Faster way. So 6.67. Then 1.99. Then and then I'll use this one.
So
Yes,
isn't that should be plus?
this will be plus. Why? Why?
Minus minus get so
Yeah, minus minus get this right. So minus minus becomes plus. This will be minus GMM over R1 plus GMM over R2. So if you take common, then GMM and then it will be minus 1 upon R1 plus 1 upon R1, R2. Or you can write it as GMM 1 over R2 minus 1 upon R1, like that. Do you understand?
okay, yes, I got it.
Okay. Goes to power 10 and then minus. Oh my god, this is very long calculation. So I'm getting change to be something like 4.23 times 10 raised to 23. That's what I'm getting. I don't know if
Yes,
that's
even I.
okay. Then state with the reason whether change in potential energy is an increase or decrease. Now, if you
Sir,
look at this, yeah, yeah.
why can't we like take the radius of the planet, like like how we take the radius of Earth? So why don't we take the half of the distance that they gave?
Yes, you're right. But you're basically missing out something. The
No,
distance we
here
look
they said
at,
the distance is 6.38 into 10 to the power of 10. So why
yeah.
not take half of it to find the radius?
Why would you do that?
Because they asked radius, and radius is like half the distance or the
Oh,
diameter.
no. For the formula GMM over R, this R is the distance from center of one object to the center of other. Like this is from here to here. It includes the radius. Same goes for this one. Includes the
Okay,
radius.
so why my question is why can't we take the value as it is? Why do we need to find the difference? Because I did directly.
No, because this value has a it has a gravitational potential energy at this point, and then it has another gravitational potential energy, so we have to subtract them. That's fine.
But did they give the distance for x?
Yes, they have this.
Oh, okay, okay. So I didn't see that. Okay, fine.
Okay. Then can state where the change in gravitational potential. You see, when it's moving towards, so basically the force it is getting is towards the Earth, right? Or the star. The force is the work is done in the favor of force, which means whenever work is done in the favor of something, gravitational, any potential energy basically decreases. If the force was opposite direction and was moving towards it, then it would be increasing gravitational potential. So we're going to say they're basically the force is attractive, right? And object is moving towards the force. So the potential energy decreases. So this is the reason when you throw something against Earth, like you throw upwards, it's going against Earth, so potential energy increases because you're going against the force of gravity. Do you guys understand this? Anyway, so then use your answer to determine speed in kilometers for comet. So you have this, you can simply use half mv square now. 4.23 times 10 raised to 23 equals to half times mv square. We want to find the final speed, right? We have the initial speed already here in kilometers per second. Interesting. So we can change this, right? 34.1 times 10 raised to 3 meters per second. That's a lot of.
It's asked in kilometers per second.
Alright. They asked for kilometers per second. Yeah, but we can't do that. You have to convert it later on as well. The reason is why, because this is an SI, this is an SI. We can't divide by kilometers then.
Oh,
You get it? Yeah. So 4.23 times 10 raised to 23. First, we're going to write half mv square. So mass was, I think, 2.2 something. 2.2 10 raised to 14. And then multiply by v square, because this is final, minus, because this is change in energy, right? So we got to find change. Half into 2.2 times 10 raised to 14 times, the speed was 3.41 times 10 raised to 3 whole square. Now you got to do this. What'd you get? We can take that common, right?
70.8.
7800 in meters per second, right? Then you have to convert, like Gatika is saying. When you convert it by dividing by 1000, so then you get in kilometers. So it will be 70.8. Yes. Thank you, Narjas. Is it clear, everyone? Now, if you notice in the next one, it says the second comet passes point X with the same speed as comet B and traveling in the same direction. The comet is gradually losing mass. The mass of the comet, mass of this comet when it passes point X is the same as the mass of comet B. So let's say the reason how the second comet compares with this. If the mass is same and it's basically has the same speed, everything is same. So then it means that path will be the same. It will be unchanged. Because everything is same. So unchanged, you can also write as mass remains same. Same at point X. Very stupid question. All right. Then the next is the Coulomb's law. Coulomb's law is that force, you can write electric force if you want to, is directly proportional to product of charge, number one. And the second part of the definition will be that force is inversely proportional to square of distance from their centers. Like that. Oh. So then Positronium is a system which an electron and positron orbit same period around the common center. The radius r of the orbit is this. Fair enough. Explain how the electric force between electron and positron causes the path of the circle to be circular. Okay, that's pretty simple. So you want to say that here you might see the force will be like attractive force, like this. So they're basically towards the center, right? So at the same radius, I'm going to write at same radius, force equals to mv square over r. So resultant force same. All right, for first point. Second point, I'm going to write the acceleration is towards center. So only direction of velocity is changing due to it. Achha, force is towards center, and you can also write one more point, and that is that you can add here that perpendicular to velocity vector, because this will tell you that obviously it's going like this, and the acceleration and force is this way. That's why it's changing the direction. Okay. Now it says show that the magnitude of electric force between the electron and positron is this. So electron and positron both have the same mass, by the way, if you don't know. So F equals to kqq over r square. 8.99 times 10 raised to 9 is k. 1.6 into 10 raised to minus 19. I'm going to square it off. Why I'm squaring this? Because these are same. You can write it again if you want to. And the distance between them is basically the radius is given. Radius means half distance. We got a full distance, right? So we got to multiply 2. So it will be 2 times 1.59 times 10 raised to minus 10 and whole square. What you get? I think you should get the same, right? Yes, exactly. Very good. You guys have any questions, please let me know. Okay. All right. So going to the next then. Use information, determine the period of circular motion. So now we want to find the period, right? So how do we do this? Probably using F equals to mr omega squared. So we're going to find omega first. So this will be F over m times r under root. Okay, so we have this force, which is 2.28 times 10 raised to minus 9, divided by mass. Now, mass is an issue, right? Well, it shouldn't be an issue because mass of an electron and positron is the same. So it's 9.11 times 10 raised to minus 31. Okay, so that would be mass. And then radius is this one, 1.59 times 10 raised to minus 10. Now we have to take radius. Minus 10th, I don't know. Minus 10. Wait. Okay, under root. Can you please find this value for me? Yeah. When you find omega, which is, I guess you guys have not done this or done it differently. 2 point.
So it's 3.97 times 10 raised to 15.
10 raised to 15 radians per second. Oh my god, that's a lot of speed. Anyway, so then omega is 2 pi by t. That's omega. So then you can just put it like t will be equal to 2 pi divided by the value that you found. Yes, please. What you get? Yes.
It's 1.58 times 10 power negative 15.
Negative 15. Okay, seconds. Pretty good. If you have any questions, please let me know. Now, positronium is highly unstable, and after a very short period of time, it becomes gamma radiation. Describe how gamma radiation formed from two particles in positronium. Okay. So basically, what happens is whenever an antiparticle interacts, right? Annihilation, annihilation, annihilation. Okay, annihilation of positronium and electron will result in release of two gamma ray photons of equivalent energy to the mass of two particles. And this can be explained further by E equals to mc squared, like that. All right. So this comes from, I think this comes from the PET more than this. So one medical application, obviously this is PET. Scan. Anything you would like to ask, please let me know. Then going to the next, it says define specific latent heat of vaporization. So it is first for thermal energy per unit mass. Thermal energy per unit mass needed. So this is 1 mark, this is second. Needed to completely change state of liquid to gas or vice versa. And the important thing is without change in temperature. This is the keyword, you should never forget it.
So can you scroll up for a bit?
Yes, please. Here. Okay.
Okay, sir, thank you.
Then it says the specific heat capacity. Oh my god, what is this? Okay. Then it says the specific heat capacity. Atmospheric pressure is given, this is given, oh my god. Mass is given, and calculate thermal energy supplied Q to the water. Okay, we can do that. E equals to LV times M. So this is the formula. The latent heat of vaporization is given as 2.3 times 10 raised to 6. And the mass is 0.37. What you get?
8.5 times 10 raised to minus 5.
Minus 5. Okay.
8.5.
8.5. Okay. So the mass is 1 mole of water is 18. Assume the water vapor can be considered to be ideal gas. Show that the volume of water vapor produces this much. Not bad. So number of moles is given by mass in grams over mr and n over n, number of particles of Avogadro's constant, right? So you have 1 mole. And this is water, right? What is this? This is not fair. 8.5 times 10 is to power 5. This much, Radhika?
Yes, sir.
Okay. All right, fine. So the thing is that we do not have, what do we have? We got to change this. This is the mass in kg. So 0.37 kg is equivalent to 370 grams, right? So this is MR. So 370. No, this is not MR. This is like 18. 1 mole of gas is like its number of moles we can find. Okay. What you get? The moles in this much gas? 370 divided by 18. That's
20.56.
20.556. Okay, so these are the moles. Then what do we have? We want to find the volume. So PV equals to nRT. We can use this. This is much better. Okay. So volume will be N will be 20.556. R will be 8.31 times temperature. Did we have temperature? 100 degree. 100 degree is 273 plus 100 is 373. And divided by the pressure, which was atmospheric, 1 into 10 raised to the power 5. What you get? You should get the same answer, right? Yes. Okay. Good going. All right. Then it says, assume that the initial volume of water is negligible compared to the volume of water vapor produced. Determine the magnitude of work done by water expanding the gas when it vaporizes. Okay. So work done is pressure times change in volume. Now we have the pressure and the volume that it caused to increase was this much. So what you get?
So 64,000. So 64,000.
64,000. Okay, very good. 64,000 joules. Then use your answers in this to determine the increase in internal energy water when vaporizes. So internal energy is given by Q plus W. Okay. So we have heat energy supplied as 8.5 times 10 raised to 5. Now we need to subtract this. The reason we need to subtract this is because it's doing work against the system. So obviously, when you do work on the system, you have to take work as negative. Okay. So what you get? Okay, Gatika. Very nice. 10 raised to 5. Okay. Then it says use the first law of thermodynamics to suggest for the reason how the specific latent heat of vaporization of water at pressure greater than atmosphere compared to value. Okay. If you have pressure greater than atmospheric pressures, then according to work done, change in this. For the same volume to go into the atmosphere, you need to do more work, right? Let's say more work done is needed to form same amount of volume of water vapor. Okay. And then you need to say that what will be the effect on the internal energy. No, it says use first of how specific latent heat of vaporization of water at great pressure. Specific latent heat of water. So specific latent heat of water basically depends on the energy. So what you do then? To increase the same amount, then you are subtracting. You need to have greater energy supplied, right? So then I think that specific latent heat would have to increase as well. So since for the change in internal energy to be Q plus W, greater work would require greater amount of heat supplied. So because Q is equal to LV times M, right? Hence, latent heat of vaporization will increase. I think. Is it clear?
Sir,
Yes.
they said explain your reasoning in the previous part. So what can we say about that?
Which you explain with your reasoning? Oh, yes. You have to reason here that work done is on the surroundings, all right? Hence, we have taken work as negative. Is it clear? All right, Narjis?
Yes, sir, it's clear.
Okay, Kartika, I'm explaining this. So, imagine this is water, okay? And now you're putting more pressure. For water to expel into air, you need to do more work then. You agree, Kartika?
Yes, sir.
If you need to do more work, then the internal energy depends on Q minus W in this, because minus means that it's basically doing work on the system and then you're supplying heat to it, right? For the same increase in internal energy, if you have greater, like you have to subtract this has a greater value, then you have to put a greater value in here so it balances out. Do you understand what I'm saying?
Yes, sir.
Now it balances out. It means that you're supplying more heat. And if you're supplying more heat, heat is related to latent heat of vaporization time mass. So you have the same mass. But if you increase this heat supplied for the same mass, you would have to have greater latent heat of vaporization then, right? This is what I tried to explain.
Got it, sir. Thank you.
Okay. Then the next question
Wait,
says,
could you move up for a second?
yeah.
Some minutes, sir.
You should try to attempt these papers in 1 hour 30 minutes. Okay. That would put you into pressure of completing this. And by reducing the
Done,
time
sir.
given, that helps you build the muscle memory for the definitions that you need to write. Okay. So then you don't have time to think. And that's good. So do make sure that when solving the paper, you time yourself, put a timer for 1 hour 30 minutes, not 2 hours. Now, what is meant by resonance? Resonance is a phenomena where external driver frequency matches with natural frequency. And when this happens, basically what happens, that amplitude, net amplitude of vibrations increase to maximum. This is what resonance means. All right, is it clear? Now you have a light pendulum, you have a heavy pendulum, 2 fixed points, and they've shown you the graph, heavy and light, fine. Then they say this is the equation and calculate the period of t. What to do? So this is x equals to x naught sine omega t. You can compare this. So omega in this is 5.0 pi. Omega is 2 pi by t. So t will be equal to 2 pi over 5.0 pi. This will cancel out. 2 over 5.0 is
0.4.
0.4. Is this answer correct?
So 0.40.
0.40. Very good. Now, on figure axis, use the space below for any. Label both axes with correct scales. Eh? What? What is he even asking? Oh, we have to. Oh, I get it. So they have. Oh, interesting. What time period did we find really? For the light pendulum, right? This is for the light pendulum. So when is the. So for the light pendulum, which is right here at 0. So at this point, we can find the maximum displacement. Maximum displacement is 0.25. 0.25 would be here, right? And this will be negative 0.25. And the time, this will be 0.40. This will be 0.80. This will be 1.2. Is it clear?
Yes, sir.
But did they ask you to draw for the other one? And you have to scale it. So this will be 0.25, then this will be 0.50, this will be 0.75, this will be 1, right? I think. From just looking at the graph, we don't have the equation for the other one. Okay. Fair enough. Now, going to the next. Determine the magnitudes of the phase difference between oscillation of light and heavy pendulum. Eh? That's not fair. What kind of question is this? But we'll find it. Don't worry. It's okay. And we have to find it in 5. We just need to find the phase difference in degree. So we can do that. I don't think so. This is very difficult. Let's do that. If this is like one oscillation, right? So one oscillation, one time period is 0.40, which is equivalent to 360 degrees. This is AS question basically. So then for this one oscillation is this much. Eh? What? Isn't it the same? It's the same. It's the same, but there is a difference in sort of other things. Let me just tell you why.
Sir, why aren't you taking the one for light?
One for light?
The difference between the light one, the light wave.
I didn't get your question really. I didn't understand.
You drew the line for the heavy one, right? The dotted one.
Yes. Here.
Why aren't we taking the distance between this like the solid line?
We're doing that. Just a second.
Oh, okay.
Angle, yeah, we're doing that. Don't worry. So what I'm going to do is I can see that this much of the part and this much of the part, they have a difference of, I think, if this is 0.4, 0.10. Do you guys agree? If 0.40 is equivalent to 360 degrees, then 0.10 is equivalent to how much? Can you cross multiply, please?
$90.
90 degrees. So this should be the answer. Be 90 and in degrees.
Oh, sir.
Yeah.
Why did you take 0.1?
Why I took 0.1?
Yep.
Both have the same time period, right?
Yeah.
But we need to see how much different they are from the position aspect, right? So if you look at this is the crest of the first one.
Mm-hmm.
And the crest of the other one is here. So the difference between their crests are of this much, which is 0.10.
Oh, okay.
So I'm saying if the total time period of both of them is this much, which is equivalent to 360 degrees, then how much will it be for 1.0? So it will be x. 3 cross multiply. Do you understand?
Alright, yeah, okay. Answer in the mark scheme, the answer is given in radians.
You can convert that into radians as well.
Yeah.
They haven't fixed it. So if you want to convert it in radians, very easy.
All right.
Pi radian is equal to 180 degree, by the way. Okay. So 90 degrees will be equal to how much? That's
Plus pi over 2.
pi over 2. Okay. So pi over 2 is you know
1.6.
1.6. So you can write 1.6 radian if you want to. 90 degree
All
is
right,
equal
sir.
to 1.6 radian. That's why. So it's all right. I don't think so. They haven't given in degrees.
No, sir, for some reason.
Okay, I don't know why, but they have also left the unit open, so I don't think so. That's gonna affect your answer anyway.
So they give two answers, 1.6 and 4.7. How 4.7?
That's the multiple of it. 90 degree plus 360 degree. What is that? Can you tell me?
450?
Okay, 450. If pi radian is 180, then what is 450? Cross multiply, please. It's basically the next phase.
So
Yes.
that is 7.85.
That's 7.85.
Yeah.
Okay, that's very strange. Then probably they've taken it like this. Let me just see why they have given. What is the answer they've given? 4.7.
7.
Okay. Then probably they might have taken it as a difference of like it started from this point. It started from this point, right? So it basically, if you take this point, what is this? This is 0.10. And the next time this forms here, this is 0.40. What is the difference? 0.30. That's the phase difference as well.
Yes, sir.
So do instead of this, write 0.40 is 2 pi radian because that's 360. Okay. So 0.30 will be x cross multiply. Check the answer to that.
Yes, sir, it's 4.7.
Yeah, that's just a way of looking at it. That's it. Where you starting. Okay, Karthika.
Got it, sir.
Okay, then going to the definition for parallel plate capacitor. Okay, so capacitor is the charge per unit potential difference. Okay, or potential. Okay, so we're gonna write this for 1 mark. The second mark is that where charge is on one plate and potential difference across both plates. So this is how it's taken. Then you have two capacitors. They say explain reasoning, and you may draw. You may draw. Okay, never mind. So you have two capacitors. In parallel, obviously you will have the same voltage. Okay, different charge though. So it will have Q1. This will have Q2. So the total charge is Q1 plus Q2. Okay, like that. Charge is equal to CV. So we're going to write capacitance 1 over V equals to, sorry, total capacitance over C. Capacitance 1 over V plus capacitance 2 over V. So V cancel out. This lets us have this formula proved. Okay, like that. Let's say explain your reasoning. So the reason is potential difference V is equal in each capacitor due to being parallel. So that's what you guys need to remember. Now, going to the next, it says show that the combined capacitance of two capacitors are this. Where are the two capacitors? This is in series. In series, the capacitors are added with the reciprocals. 1 upon 22 plus 1 upon 47 equals to 1 upon C. So what will be the C? I think it should be 15, right? Can't go wrong with this.
Yes, sir.
Let's say two-way switch is initially positioned at X. So it's charging the capacitors. And so the capacitor is fully charged. Using information, calculate the total energy stored in this. So you have the total capacitance. Energy is half CV squared. Okay. So total capacitance is 15 into 10 raised to power minus 6. And the voltage that is supplied is 12. 12 squared. Can you find this, please? Hmm. 1.1 times 10 raised to minus 3. Very good. Then two-way switch is now moved to position Y. Determine the time taken for potential difference across 22 capacitor to this. Oh, determine the time taken for potential difference across 22 capacitor to become this. Whoa, this is interesting. So first of all, we need to find how much, what is the potential at that. So you have the total, you have total as 15, and this is 22, right? So what you're going to do is, there are a couple of ways of doing this, though. We have to find the initial potential there. So we want to find this. We don't have the total charge as well. Interesting, huh? Total capacitance, we don't have the total charge. There has to be ratio. We can take the ratio method, or you can do the other method. So ratio is much easier, but chalo, never mind. 15 into 10 is to power, let's do 15. Voltage is 12. What is the total charge?
So 180.
180 microcoulombs, right?
Yes.
And then you can use Q is equal to CV again. Charge basically in series remains the same. So charge on this could be charge on this. And the charge is always taken with respect to, yeah, okay. So then, never mind. So capacitance on this one is 22 microfarad, and the charge is 180 microcoulomb, and we want to find what you get.
8.2.
So that would be voltage. Other method of this is like you can do 15 divided by 22. That's the ratio times, this is the 15 out of this, and then you can multiply by 12. You can also get it this way, but that's a ratio method. If you like it, you can do it. Anyway, so then what you need, we need time. So we have to use the exponential equation. V equals to V naught E minus T over RC. So initial, it has dropped to 6. This is 8.2. E minus, we want to find this T. The resistance. Whoa. We don't have the resistance. Do we have the resistance?
We do, sir. It's 2.7.
Oh, 2.7 mega. Where is it? Okay, so 2.7 times 10 raised to 6, and capacitance is 22 times 10 raised to minus 6. Okay. Can you find this, please? If you don't know how to do this, you have to do this. Take ln, and the other side, this will be minus t over 2.7 times 10 raised to 6, multiply by 22 times 10 raised to minus 6, and multiply by ln e. Ln e is just 1. Yes, what you get then for time?
Say 18.55.
18.55?
But sir, that's not the correct answer.
Why? This is not fair. What mistake we have done? Wait a second.
Sir, the capacitance used is 15, not 22.
Yes, that's true.
But why, sir? It should be the same, no?
It's no. Basically, the thing is that the voltage we have taken is basically this whole capacitance affects this, right? So some charge is coming from here, some charge is coming from here. That's why we have to take the whole one. That is the reason.
Now it's 13, sir.
13? Should be 13 seconds. Okay. Check Maxim, is this the same answer?
Yes, sir.
Yes, sir.
Yeah. Because the thing is that why it says potential difference across 22 becomes 6. We have to take the overall capacitance. The reason why we're doing this because energy from this capacitor and that capacitor basically moves through this, and they're sharing this resistance. If the resistance was like only for this one, then we would have taken. So we have to take the total capacitance. You have to take the total capacitance here. You get it? For the total resistance here. That's why. You get it? Now? Now, state two condition that must be satisfied copper wire placed in magnetic field to experience a magnetic force. Copper wire, there must be obviously current and perpendicular to it. So current in the wire and should not be 0 degrees or parallel. If it's not 0 degrees or parallel, then obviously you will have force because F equals to BIL sine theta. Theta, if you put 0, then it is 0. Otherwise, it's not. Then, a long air cord solenoid. Okay. There is a solenoid wires, and this is what is this? Direction of magnetic field. 3 points are X, Y, Z. Draw arrows to indicate the direction. Okay. Now that's good. But I don't know where the current is going and coming from. That's not fair. You know? Okay, one of the directions given. Okay. So it means that then if this is going this way, so it always goes from inside, it has to be north. This has to be south. You guys agree? Within the core, the field is like it's parallel. So X and Z has to be parallel. Sure. Here it would go like this. So it should be like this, and it should be like this. Do you guys understand this? That's why it should be this. How did I know? I used basically right hand grip rule. This is Maxwell rule I use because I know if the field is like this, so inside goes from south to north, so it has to be north here. So my thumb should be here and my fingers should curl this way, which means this is like current is here, current is into, and this is like out. This is I should be knowing. Anyway, so it says compare the magnitude of flux density of magnetic field at X and W. So within the core, they're parallel and they're equal distance, so they will be same. And Y and Z. Y, the magnitude Y, because here the field is stronger and then here the field is weaker, so greater at Y than Z. That's all. Okay. This is O level question. Sir, for Y, it says the arrow should be pointed towards left, like this. Yes, it should be like this. Sorry, I did not follow the field. You have to follow the field, Kartika. That's correct. It should be in the direction of field. That's fine.
So could you please explain part 2?
This one? Okay. So
Yes, sir.
whenever you're looking at a solenoid, okay, Munir? I just want to tell you, within
Yes,
the solenoid, the field is like equidistant and parallel. So it means that any point within the core will have same magnitude. Okay.
All right.
But when you see outside, they go like this. So this region has the lowest and this region has the highest compared to each other. So
All
it
right.
means
Okay.
one will have greater, this will be have lesser. Understood?
Okay. Yes, sir.
Now, two parallel current carrying wires are placed near to each other in a vacuum. Explain why these wires exert a magnetic force on each other. You may draw a diagram. Okay, this wire, this wire. So if this has a current I1, this has a current I2. So this field, the field of this one, how you draw this is by grip rule. So you can make concentric circles. This will be the field. And obviously at some point, the field is going to go like this, okay? Interacts with the other one. Let me make this wire closer to this, okay? Like that. Okay. So then I'm going to say, if I were you, because the field direction is like this, how do I know? Right hand grip rule. Thumb up, and your fingers will curve like this, okay? Like that. So then here, the field is like into the wire, the current is there. So now I'm going to write it this way. I'm going to say wire with current I1 creates a magnetic field. Okay. Then for the other mark, I'm going to say the magnetic field of I2 and I1 interact by each other. Number 3, since the field is perpendicular to current, then according to F equals to BIL, right, both wires experience an equal and opposite force. Is it clear, everyone? That's all. So these diagrams are already made in the notes. So when you go to the magnetic field chapter, you'll find these. You can review them if you have done this wrong right now. Okay. Going to the next. State the Faraday's law. So Faraday's law is that induced EMF is proportional to rate of change of magnetic flux linkage. That's what you're right. Okay. Now they've shown two coils, one with the supply and one with the voltmeter. And they've shown a variation of magnetic flux P. Okay, fine. Voltmeter measures the electromotive force V2 across 2. Fine. This is what you do. Now, this is EMF, this is magnetic field, and this is basically EMF. So EMF is minus change in magnetic flux linkage over change in time. Okay. Now, whatever the gradient of this is, gradient of this is value in this. Okay, you got to remember that. And it has to be negative as well because it is negative sign. So first of all, we make it three sections. So from this to this time, which is I think 0.15, it is what gradient? Constant gradient positive, right? So we're gonna draw it as constant gradient till 1.5 and negative. Do you guys understand this? Then the next section is constant gradient and negative. Also, it's steeper than the first one. So it's basically stays from 1.5 till 2.5. Okay, 0.25, which is this one. So I'm going to make it positive and higher value. Like here. Okay, and just make a dotted line just so to tell the examiner that you know. And then this one, third mark, third is like positive gradient. And I think it's the same like gradient. So it's from 2.5 to 4. So same line in the negative section. Because it is positive, it has to be negative. Do you guys understand this? Okay, you guys understand?
Yes, sir.
Just do this. It's very simple. And then coil 2 is replaced with loosely copper ring with the rest loosely on top. The switch is now closed, and the copper ring observed to jump upwards. Why this happens? Okay, that's pretty easy. So when the switch is closed, coil 1 produces magnetic field. Okay. Then this causes a change in magnetic flux linkage to the copper ring. That induces current in it. 2 marks. And then, according to Lenz's law, we were right that the magnetic field produced in copper is such that to oppose the change causing it, hence it repels. Like that. Is it clear? It moves upwards, whatever.
So can you read the second point again?
This causes a change in magnetic flux linkage to the copper ring that induces current in it. Okay.
Okay, sir.
Then say, sir, with the reason, what would be the effect of repeating the procedure with the terminals of cell reversed? It doesn't really matter.
Sir, what's the last line?
The
Could you read
magnetic
it out?
field produced in copper is such that to oppose the change causing it, hence it
Oh, okay.
repels. Okay. So it will still jump up. So whether you create a north pole here because of this coil or south pole here, it will always create south when there's north, and it will create north here when it's south. So it does not matter. It will always oppose it. So that's why it will always jump up. It doesn't really matter even if you switch the terminals. Okay. You guys understand? Any questions here?
Sir, it says with a reason.
Okay, so it will still jump up. All right, I'll tell you then. Okay. The current, okay, reversing the terminals will also reverse the direction of current induced in ring. You can write that. Okay.
Sir, can you explain this part again, please?
Yes. So I'm going to explain this differently. So suppose this is a coil, it creates a north, okay? It is creating a north, Kartika, okay? Like this. So the ring that you see will create a north here to oppose it. Do you understand? Like that.
Yes, sir.
Now if you like this was positive, negative. If you repeat this, like you put negative here and positive here, now it will create south here. So it will create south to repel.
Oh, okay. Got it.
Because Lenz's law says whatever the change is, it's got to oppose it. So no matter what you do, it will repel. You understand?
Yes, sir.
Okay. Then going to it. State one piece of
Sir, could
evidence.
you go up?
Yes. Okay. I need to stretch a bit as well. Oh, all right, good. We can go forward now.
Could you read the second line, please?
It will still jump up. Reversing the terminals will also reverse the direction of current induced in the ring. Okay, you get it?
Yes, sir.
Okay, now going next. So, state one piece of experimental evidence of particulate nature of electromagnetic. This. Okay. Photoelectric effect. And then says wave nature of matter. De Broglie electron diffraction. Okay, then calculate the de Broglie wavelength. Alpha particle moving at speed. So it is h over mv, 6.63 times 10 raised to minus 34. Mass of alpha particle is 4u, which is 1.66 times 10 raised to minus 27. And for this is mass and the velocity is 6.2 times 10 raised to 7. What you get?
One 1.6 times 10 to the power of minus 15.
Yes. Okay, that seems about right. The speed of alpha particle is gradually reduced to zero. Sketch a variation of lambda. Okay. Speed lambda is like inversely proportional to speed, right? Everything else is that, right? So it should be like this. Downward curve. And it should not, like at zero speed, will it have a wavelength? This is interesting. Let me think about it. Yes, it would have, because then, but how? Is 1 upon 0 infinity, right? It's infinity or zero. It's infinity.
Yes, sir,
Right.
it won't have.
Yeah, it won't touch the axis then. It would be like this. It should be like this. Is it clear? So yeah. Then it says suggests an explanation why people are not observed to diffract when they walk through a doorway. Okay. Interesting. If the mass, like the de Broglie wavelength, is this, even if we have a lot of speed, like we have less speed, but we have a lot of mass as well, right? We do have some wavelength, right? If you have a lot of mass, your wavelength is going to be very small, don't you think so? Your wavelength will be smaller than even alpha, beta, gamma, whatever. So that will mean that doorway cannot diffract. And the reason is because for diffraction, the lambda should be almost equal to the slit opening. So wavelength of humans is very small compared to width of door. Do you guys understand what I'm saying? That's why. Cool, right? Then we're gonna go to the next one. States Hubble law. Okay, speed of recession is proportional to distance of galaxy observed. Okay. And that is it. Now, explain how cosmologists use observations of emission spectra from stars in distant galaxies to determine the universe is expanding. Okay. So, what you do that cosmologists observe wavelengths of shown in a spectrum at Earth in a lab. Okay, this is what you do, and then compare the same spectrum coming from a distant galaxy. It seems red shifted. Red shifted means that the movement is away. Hence, they are moving away from Earth. That's why it's expanding. Is it clear, everyone? Then says explain how Hubble law and the idea of expanding universe lead to Big Bang theory of the universe. So, okay. So from redshift, we observed that universe. Okay. All right. Objects in universe are all moving away from each other. Number one. Number two. The greater the distances, the greater their speed of recession. Okay. Third point, it means that they originated from a singular point of very high density in the past. Is it clear, everyone? Let me know if you have a question. All right. So we got like only 7 minutes. How many questions this has? Oh my God. One more. Okay, we can do this. Okay. So now we are looking at radioactivity. So what is radioactive decay? So radioactive decay is the disintegration of an unstable nucleus by emitting a radiation. This disintegration or this decay is random and spontaneous. So you write that. That would give you full marks, I think. And then you have this. So it says radioactive consider isotope X. Isotope, the half-life T that decays from. So half-life is T. Radioactive sample consists of isotope X of half-life T that decays to form a stable product. Only X and the stable product are present. At time 2, the sample has an activity of A naught and N naught contains. Okay, so it starts here and sketch. So T, it will be halved. So this will be here at T. And then at 2T, it's going to be halved again, which is going to be here. And at 3T, it is going to be halved again. So this half will be here, right? That's it. So you're going to make a smooth curve like this. Okay. Now, then says on variation, activity of sample N. Oh, wow. This is not good. This is something. Okay. This is, I think it's the activity. Basically, the formula is N equals to N naught E minus lambda T. And A is equal to A naught E minus lambda T. So I think it's comparable. Like, we can compare N over N naught equals to A over A naught. So it basically means that they're like, it has to be straight line, they're directly proportional. So at this, they will be same. At 0.5, they will be same at this. So you got to make a straight line starting from origin. That's how it should be. Now, it states the name of quantity gradient of this. I think if you look at the situation here, A ratio N is basically decay constant because A is minus lambda N, right? Like that. It's decreasing curve. So, oh, in 10.1, sorry. 10.1, the decay will be N, change in N over change in time. That is activity. And here it is decay constant. Then says for sample fraction N time 1 naught T. Calculate the fraction of N. So N over N naught equals to E minus lambda T. Now the issue is, do we have the lambda? We don't have the lambda, right? This is not fair. This is not fair. So, okay. So what do? We can find with the half-life. So ln2 over lambda is equal to time of half-life, right? Time of half-life they gave us is T. So lambda will be 0.693 divided by T. Okay. Or we can write ln2, that's easier to manage. Okay. So n over n naught E minus lambda will be ln2 over T times this T is 1.70 T. So T and T will cancel out. ln2 times 1.70. What you get for this? 0.31. Okay, very good. This was not bad. Not bad. Okay, this is good actually. All right, so we're done here. Now, I think if you go to the, I opened for AS, I'm going to check this. This is 4.2. If you scored 54, total it up, it's good. But you should be aiming till 70 at least, okay? And yeah, we're done with here. Now, that's it. I just need to talk to Faisal and everybody else. If you have no question, you guys can go. It's all right.